Hi, this talk is ClojureScript on microcontrollers. It's really about running ClojureScript on a relatively new chip named the ESP32 using a JavaScript engine named Espruino. I'm Mike Fikes, and this is for Clojure North 2020. Before we get into the details of this, I'd like to thank my company, Vouch. They've been there for me in terms of making sure I have plenty of time to do this, but also making sure I have all the tools I need to pull this off. And as you see as we go through this, Vouch is kind of interwoven in the story. Okay, so I'd like to give a little bit of motivation for this. So in the picture on the left, you can see that there's a Raspberry Pi, and that's great for us because it's effectively a computer. You know, it's got Linux in it, and you can run Clojure inside of the JVM on it, or you can run ClojureScript inside a node. And the thing is portable. You know, you can put it wherever you'd like. And at the time, Vouch was getting into using, and the picture on the right is a CAN shield that's on top of the Pi, that board that's on the top. CAN stands for Controller Area Network, and it's used, you might recognize that's an OBD2, onboard diagnostic 2 plug that you can plug into a car. And at the time, Vouch was beginning to investigate using, expanding our digital identity product into cars so that we could use them to lock and unlock cars. And we were effectively doing that with the Pi at the time. And you know, the Pi is great because you can put it in your car and it works in there. But it's also kind of a bit clunky. I would have to drag out one of those big orange extension cables out to the car to power the thing up. And I'm pretty sure you can power it from the car itself. But it's also kind of evidently fragile. You have to be careful to make sure you shut the thing down properly each time. I did lose my flash drive once, and it might have been because I wasn't doing that properly. And also, if you're going to demonstrate this to someone, a Pi just doesn't look that good. So that's where we were at the time. So to improve this situation, around that time, Vouch started working with Bill Hurd. And if you don't know Bill Hurd, he, back in the day, designed several Commodore computers. So he knows a thing or two about production electronics. And I suppose the fraction is dwindling in the audience, but I suspect a good fraction of you may have actually used those computers back in the day. Or perhaps maybe I'm just dating myself. But anyway, also more importantly for us was that Bill had experience with automotive grade CAN bus stuff. So at the time, Vouch had some pretty aggressive delivery deadlines, and working with Bill, he suggested a chip that I had never heard of before called the ESP32. And the picture on the left there is what you might get if you were to buy an ESP32 off of either Amazon or say eBay. And it's actually like a development module. It has a USB jack in the bottom, and it's like a self-contained thing. It has header pins on the left and right. Those are GPIO, general purpose IO pins that you can use to have the ESP32 drive things. And it's actually, importantly for us, is it actually has Wi-Fi and Bluetooth, BLE, Bluetooth Low Energy, built into it. And also, to top it off, it has a CAN controller ability built into the chip. So in this one single chip and this nice little package, it met a lot of our needs. And the middle picture is what you might get if you were to buy these ESP32s by themselves off of, say, DigiKey or Mouser. If you were to get just the module itself. And on the right is actually the ESP32 itself is actually a little chip inside underneath that RF CAN. If you were to take that off, that picture on the right is showing what it looks like inside there. And the ESP32, you could actually, buy that little rectangular chip itself and use that. And I think the other chip that's on there is maybe the flash chip. But that's actually the ESP32. And also interesting in this picture, you can see along the edge there is the PCB based antenna for the Wi-Fi and the Bluetooth. That's that little meandering trace that goes. It's called an inverted F antenna. But that's how this whole thing is like one self-contained package that does all these things. So Bill went to design an industrial strength solution, but I proceeded with prototyping and used an ESP32 to effectively replace the Pi that I had been previously using. And importantly, in this picture here, you can see it's stuff on a perf board. There's an ESP32 on there. The little blue thing at the front is a CAN transceiver, and importantly, it connects to a DB9 connection, which is the very same connection to the OBD2 port that the Pi's CAN shield would connect to. And with this was actually already by itself a big improvement over the Pi because well, first of all, it was a little bit smaller. You could plug the thing directly into the car. It actually would get its power from the car. In the upper left is a little voltage regulator that could take the 12 volts from the car and convert that to the 3.3 volts needed by the ESP32. So it would fit directly in the car. No need to drag out that big orange extension cable anymore. And it actually booted up instantly. The Pi, it's no big deal. It would take like 30 seconds or so to boot up. This thing, the ESP32, when you put code in it, it's pretty much, it loads it from its ROM and it goes. So this prototype was already looking very promising. So having created that prototype, the next natural thing to do is to make an actual PCB for it. And Bill helped me a lot with this. So on the left is actually a layout for that PCB done in a CAD program. And if you look closely, you can see some of the same components on there. There's the ESP32 on the right, and there's a voltage regulator, and the DB9 you might be able to see is all on the far left. And this is what that ultimately ended up looking like, making a PCB out of it. And already this is actually, it's even getting smaller, and it just looks cooler. It like fits right on the end of that cable. And if you had to actually demo this to someone, it actually is starting to look a lot nicer than that perf board thing that we had previously. So I thought that was pretty cool. So if you were observant in that last picture, you may have noticed that a lot of the components on that PCB were what are called through-hole components. For example, like the resistors look like what you think of as actually like traditional resistors with the leads coming out both ends, and you put those through the PCB and you get out your soldering iron and you solder them on. So the next level up in terms of coolness and size reduction is to actually use surface mount components. So this is a PCB I started working on that use things that way, and it's essentially like those little things there are the little black things are resistors, and the other ones are capacitors. They work pretty much the same way as the other ones, as the through-hole ones, but they're just a lot smaller. And more importantly, actually, it looks a lot more like a real PCB that you might want to demonstrate to someone. So this is another example of one that was completed that has an ESP32 on it. And most of those components now are actually like surface mount components. I just think that looks really cool and really professional. Okay, so to top it off, Bill had designed his board to, this is Bill's board here, to go inside of a metal enclosure. And this just, in my opinion, looks really nice. It looks like a real product now. And more importantly, the thing is like a tank. It's really tough, really robust. So I've been using these in my cars for the past half year, it seems now. And that's one way to actually dog food your product is just to use it day to day, right? So these allow for that, and it's pretty awesome. Okay, with that background, you might be starting to wonder, Mike, what does this have to do with ClojureScript? So rolling back during this entire time, actually even previously to this, we were aware of this engine named Espruino that could be used to run JavaScript on microcontrollers. And I had messed with it a few times, never really had much success. But now that we were using the ESP32, I went and looked, and I found that the Espruino engine was supported on the ESP32. So I went and tried it again, and this time I was sure I was going to get this to work this time. So I went and built a little bit small ClojureScript program and ran it on there, and lo and behold, it actually ran. So in this tweet here, you can see that it's spitting out a keyword, and it's spitting out the number 15129. And that number is what you get if you evaluate this beast of an expression there. So that that was my litmus test. The fact that it ran that thing convinced me that Espruino can indeed run ClojureScript. So I was excited about that. Okay, so let's talk a little bit about this Espruino thing. It's essentially a JavaScript engine that runs on microcontrollers. And the way it works is you'll make a connection to your microcontroller, typically through a serial port, and then you can evaluate JavaScript expressions on your microcontroller directly, effectively a REPL. This is the Espruino IDE. So this is much better than the normal pattern you would have if you were developing typically for microcontrollers, because typically you'd be using something like C, of course, and you could have debuggers for C, which you can do step-by-step debugging and whatnot. We all know that. But with Espruino, you just evaluate stuff and it runs directly on the chip. No need to compile. And what Espruino is really doing is it's really optimizing itself for the complete lack of RAM that these microcontrollers have. So instead of doing things like JIT compiling the JavaScript to the machine language of that particular microcontroller, what it actually does is it just simply interprets the JavaScript. And on the Espruino site, there's this argument that is made where it shows a particular algorithm that's written in C and also written in JavaScript. And it looks at the minified JavaScript and it compares it to the bytes or the machine language that you might get from the C. And the minified JavaScript's actually smaller. So that's kind of what Espruino and why it's doing it that way. It's basically really trying to save RAM every which way it can. But what's kind of interesting is I think you and I, we know a language that can be more compact than JavaScript, right? So that's an interesting thing that might occur someday. Okay, so even though Espruino is really good at trying to minimize RAM use, what I wanted was, a ClojureScript REPL into the thing. And the way, at least the normal way a REPL would work is you need to have the ClojureScript standard library available to you in the target execution environment. So what that means is if you think about it, like if you were to say evaluate map inc over the vector 1, 2, 3, that indeed does get compiled down to JavaScript, and that JavaScript is pretty small. But if you look at that JavaScript, what it's actually doing is it's calling the ClojureScript runtime functions like CLJS core map. It's calling that. It's calling inc, and it's got code to construct a persistent vector. So all of that kind of stuff is actually in the standard ClojureScript runtime library, and it's pretty big, So that is a challenge for getting a ClojureScript REPL into these devices. It turned out that while I started digging into this, Philip Meyer contacted me, and he had just given a talk at the Conj about microcontrollers. And he was aware of the fact that the ESP32 comes in two variants. There's this smaller one called the W Room or Room, I don't know how to pronounce that. And then there's another one, the W Rover. And that bigger one has much more RAM. It has like 8 megabytes of RAM in it. So I immediately ordered one of those and started messing around with that to get a ClojureScript REPL into that thing because it's plenty of RAM. So, if I remember correctly, this is, I think, probably the first picture I took of actually a real REPL running in the ESP32. And if you look closely, you can see that one, that can shape there is more rectangular. That's the W rover. The W room, the smaller one, is shaped more like a square shape. So that's the visual way you can tell the difference between the two. But this is pretty cool. This is actually like a real REPL running in that device, connected in evaluating forms, which is amazing. Okay, so since we have such a small device, it's interesting to look at the power consumption of the thing. And here's a picture showing, I actually have a REPL running into it when I took this picture, and it's using just 140 milliamps, which, at 3.3 volts is like less than half a watt for this REPL. But truth be told, this is actually a lot of the a lot of the power use is due to the Wi-Fi. If instead you use just BLE, you can get the thing down to like 20 milliamps. And that's important if you have it plugged into your car and you don't want it to drain the battery in your car. So that's nice that these things don't use very much power. And also, it's kind of fun to play a game and see how small can you make a REPL be. So if you're curious, these are like the actual connections that you need to make to it to actually bring the chip up and bring it to life, and communicate with it. You need to give it power, and you need a few more connections to bootstrap it, and a few more to receive and transmit to it and talk to it. But in the end, once you have that thing going, I think the picture on the right is actually the smallest I've ever seen a REPL, ClojureScript REPL B. Truth be told, you have to actually have a computer to talk to it. But come on, this is actually the target execution environment that's really small, pretty self-contained, smaller than a mobile phone, for example. All right, anyway. Okay, so what changes were needed in ClojureScript to make this actually work inside this device? For ClojureScript, there were none. So I guess if that's the topic of this talk, I guess we could all just go home now. But truth be told, there was some stuff that had to change to get it in there. The main things were just actually a couple minor tweaks inside of Espruino. One of them is when you run Espruino on one of these larger W rover ESP32s, it has basically an upper bound on the heap that it uses for what it calls JS Vars, and that's set to 20,000. And it turns out, if you want to initialize the ClojureScript standard library, that consumes JS Vars in order to parse all that, load it in or whatever it's doing there. So you need more than 20,000. And I found that if you set it like around 60 to 80,000, something will cause the whole thing to crash. But if you choose a number around 55,000, you have plenty of room for ClojureScript itself, which I think is around 30,000 Vars. So that's one small change, just kind of like give it a little more headroom. And then another change is the way things work with Espruino and the ESP32 is the flash has partitions. And here, this is the partition table that's being used by Espruino when it loads stuff in. And the solution that I went with, Espruino has a way to save code to a certain partition. So what I did was I said, that's where I want to put CLJS core, because it's this big chunk of code that you need to load in order to have a REPL. As a matter of fact, that code takes about 15 seconds to load. It's so big. And it won't fit inside this 256K that's allocated there by default. So I effectively just kind of swapped the allocation used by the JS code partition and that storage partition. I just kind of moved that hexadecimal pointer down for storage farther down, giving it much more room for CLJS core to fit into the JS code partition. So I've taken these few changes along with, you have to actually, once you've compiled ClojureScript core or anything that you're building, in fact, you need to kind of turn it into a bin file, or I like to call it just a ROM file that you put into the mix. So I have tools in there So I've taken all this stuff and I threw it into a repo on GitHub named Esprit. And you might wonder, what's the name? So there's ESP32 and there's Espruino. So I thought I would just add more to the confusion and pick another name that starts with ESP. So Esprit, like it or not. So in there is a REPL and everything you need to get going. You can basically use this to fire up the same thing that I was showing you on your own WRover-based ESP32. Okay, so I've been focusing mostly on a REPL, but I have messed around a little bit with advanced to see what that means. And one problem that you'll run into if you use advanced is that Google Clojure uses JavaScript labels to, I suppose, optimize the code gen that it makes to make smaller code somehow. But the problem is Espruino does not support JavaScript labels. There's an actual ticket in the Espruino repository for that. So what I've done is in the tools that I have in the Esprit repo, I have a little kind of a naive solution that just goes in there and tries to strip out labels. It turns out that if you look at them, it looks like they're just kind of there and they're not really semantically meaningful most of the time. So I've done that, and I've gotten things to run with advanced, even though what you probably really want is, something that parses apart the JavaScript and does the right thing and removes the labels in the right way. And speaking of that, Espruino is really not completely 100% JavaScript compliant. It actually makes some trade-offs here and there to try to do the best for what its goals are, to try to run really well on microchips or microprocessors. One example of that is if you look at a floating point number in there, it's actually not a double, it's a float. So if you look at math pi or whatever, it's actually shorter. And for most uses, that doesn't really matter. But just to be aware, Espruino is, if you expect it to be 100% JavaScript compatible with everything you're used to, it's not. And another area for us, another small example is like regexes. Some of those don't parse properly or something like that. But for most of the stuff I've been messing around with, the simple things that I just want to get to run on a microcontroller, they work. That's exactly what Espruino is trying to do. And another thing I've noticed is, you can get things to launch even quicker with advanced because there's less code to load. You're not trying to load the entire ClojureScript standard library when you build an advanced build because you have dead code elimination. And there was one experiment I did where I had a pretty small program. It wasn't really like a hello world, but it was like a small, evaluated a few things, and calculated some stuff, a fairly tiny program. And I was looking at it and I'm like, is there a way to get rid of even more of the code that gets spit out even out of Clojure? And I don't know, but what I found was that there does remain actual dead code that the Clojure compiler can't statically see is not being called. But you can dynamically find out, you can remove that code and make sure your program still runs. And for the small program that I was messing around with, I want to say I got rid of it was all the way down to 1/8 of the original size or so, something, almost like an order of magnitude smaller. I was chatting with David Nolan about that. He proposed that perhaps that's not the case when you run into larger non-trivial size programs. So anyway, that was just an interesting thought that I had that if you're really trying to cram stuff down into really tight spaces like these microcontrollers, you might start to play funky games like that to try to get rid of every last bit of code you can. Okay, so given all this, I decided that I wanted to have my own custom board. You could think of this as an example application of how you might use ClojureScript with the Espruino ESP32 combination. And so my example application is a REPL, and I wanted it, I started thinking of requirements for this thing, and I wanted it to be a battery powered REPL. Which means that you should be able to unplug that USB jack and communicate with it using Wi-Fi. And I also wanted it to be rechargeable. I think a lot of these ESP32 boards support running off of batteries. These are these lithium ion polymer batteries, LiPo batteries. But I don't know, to be honest, I don't know if those boards actually recharge your battery. So what I wanted it was so that it would actually charge the battery while the USB is plugged in, and when you unplug it, it's running off the battery. That was my requirement for myself. And of course, I wanted to have some onboard LEDs, and just to be able to do things pretty easily. You want to sometimes do more than just evaluate stuff. You want to light up some lights, and I wanted to have some custom LEDs on there as well to let you know, like when you're connected and when you're reading, or like if you were evaluating a long-running form, I wanted an eval light to flash. And finally, the most important requirement of all was I wanted to have the ClojureScript logo on there. Why? You want to keep Chris Oakman happy, so that's why. So I started to design this board, and here is actually, like, I went through a couple of revisions, and this is what it looks like in the CAD program for the latest revision of it. And here is what it looks like in a 3D rendering in that CAD program. And not to get into this too deeply, but if you're curious, if you look at that board, in the lower left near the USB jack is some circuitry dealing with USB, surprisingly. It's basically converting USB to UART serial stuff so that it can talk to the ESP32 at the top. And then on the left there is the LiPo battery jack. So a lot of the circuitry surrounding that is, there's an IC there to charge the battery when you're on the USB. And down closer to the lower right is a voltage regulator. So a lot of the power stuff is running across the middle of that board, if you're curious about this kind of stuff. And there's some LEDs along the right and some LEDs running up along the left that I mentioned, like the connection light and the REPL lights, if you will. Okay, so here's what it looks like when you get some of these PCBs. That's an actual PCB there. And this might be interesting to you. The thing on the right is a stencil. And you could sit there and hand solder the surface mount components onto the PCB. It works, you could do that. But it's more efficient to take this stencil and you put it on the board, and then you use what's called solder paste to put basically solder on the board. It's in a paste form. It's like little solder balls inside there. And then you can place the individual components on there and it sticks to the paste. And then you can basically heat up that paste either with hot air or in a reflow oven. And it kind of melts it, and then the components go into place on there. So here is a picture of me making some of these boards. And it's, like I said, effectively lots of these little surface mount components going onto the boards. And here is one, I think probably the first one that I made, a picture of that there on the right. So here is testing these boards. What I find interesting is like comparing testing hardware to software testing, right? One thing that's interesting is like you're testing like your hardware design to make sure that it actually works. So here I am testing the battery, and I'm measuring on the right, picture on the right, measuring like the battery depletion over time, making sure that your design actually works, right? Conceptually. But then there's another kind of testing, which is like each and every individual board could fail in its own way. And it's like each one presents a little puzzle that you have to solve to figure out, like, oh, there's a solder bridge here or there, stuff like that. Something that doesn't happen in software, right? When you write some code, unless it's like non-deterministic stuff and threading, typically your code works the same way each time. Not so in the hardware world. You may have gotten lucky with one particular board working, and there could be something fundamentally like a solder bridge or something like that that's causing it to fail. Okay, so I've been talking a lot. Now it's time to give some demos of this stuff actually working. Here I am flashing the various things to the chip, the Espruino engine, the CLJS core, all go into the various partitions that they need to go into on the flash. And then after that's done, the chip will reboot. And I'm going to connect to it using Screen. Screen will establish like a serial connection to the device. And by doing that, I'll be connected directly into Espruino itself. Okay, now this is an Espruino, and you can evaluate things like you're in a JavaScript environment at this point. This is Espruino itself if you were to use Espruino directly. And you can look at process memory. And here you can see the 5500 Vars that I was talking about. ClojureScript core is using 3260. I'm going to copy this line and connect using the Esprit REPL. And then we'll be in ClojureScript. And we can evaluate forms in there. Things just work. So let me define a map form, because we love maps. This should convince you that it's actually evaluating stuff in there. If I can associate to the map, it's pretty much a full-fledged ClojureScript environment. Okay, so now if I go in and unplug it, now it's connected only using, well, it has been working off Wi-Fi. This basically proves that, it's basically not using the serial port. I can evaluate something that takes a little bit longer. You can see the eval light flashing while it's evaluating that. It can do that because the low-level parts of the chip are actually driving that light rather than the higher-level core. I'm going to basically make it light up the LEDs along the right there. I have to set it to false. It's the opposite of what you might expect because I have to pull it low to turn the lights on because of the way they're wired up. And if I write true, it'll turn the lights back off again. Okay. I can demonstrate using the lower level part of the chip that I was talking about to actually pulse width modulate a particular light. I can set the duty cycle and the frequency, set that to 1 Hertz. And discard the result of this call because it messes up the REPL if you see that. So now that light's flashing at 1 Hertz. Change it to 5 Hertz. And while that's going, I can actually go evaluate something else. Let me evaluate this long running form. And then you can see that the light's still going. That's because, like I mentioned, it's a lower level part of the chip that's doing the actual flashing, while the higher level is doing the JavaScript, the main core. And set this back to 2. Change the duty cycle. If I set it to 0.1, you see it's mostly on. Set it to 0.9, it's mostly off. And then if I exit the REPL, you'll see the connection light will go off. Okay, so that was demonstrating just using the REPL and the LEDs on it. Now I want to set things up and show you actually locking and unlocking a physical solenoid-based lock. And the cool thing about this is that it's using a lock that is driven by 12 volts. Much more power is going through that lock than what the ESP32 can deal with. So it's kind of like an example of like a small microcontroller controlling something larger, if you will, using a power transistor. That's the circuitry for it. Okay, so I'm going to set up a few helper variables to keep track of things. The lock controls connected on D19. The LED is on D22 that I want to use to indicate the lock. I'm going to define a little helper function just to make it easy to turn things on and off. And discard the result. Okay. And then I'm going to define a lock function that would set the pin for the lock control to false with the way it's wired up. And I'm going to turn off the indicator, set that to true. Okay, and then I'm going to do unlock is basically the opposite to those two. Okay, so now with these two functions, I should be able to unlock the lock. All right. And lock the lock. Okay, and then one last demo. In the previous demo, we were using the REPL to control a lock. I want to use something to control the ESP32 device. And to demonstrate that, I'm going to use a couple of, these are really cool. These are ultra-wideband devices, and they can do really precise ranging to each other. They have extremely fast clocks in them, and they have 42-bit counters, and the clocks are running like gigahertz rates. And it's so fast that it can actually measure the time of flight in terms of the speed of light going from one device to another, there and back. And from that, measure distances down to like centimeter accuracy. With that, I'm going to set this up and show you this working. Okay, so I'm going to define a function that looks at line 18 to see if these two devices are close to each other. Line 18 is where it's driving at high or low. And right now, they're not next to each other. Put them close to each other. Now we get true when they are next to each other. Okay, so now I'm going to define a function that essentially just loops over, checks to see, are they close? If so, unlock. Otherwise, lock it. And just keep looping, recur. Okay. Put the device close, remove it. So this ultra-wideband stuff is stuff that we're dealing with at Vouch. I think it's pretty cool, cutting-edge technology. You know, it's crazy insane how well they can measure distances to each other. So I think that's pretty cool. So these boards, I've put them up in GitHub if you want to get at them. They're all open source. The schematics, the Gerbers, you can print them out. The BOM is there so you can get all the components if you want. And if you just want to buy one as well, I have them up on Tindy. My intent is to try to make them, to price them so that they're not making a profit. And to be honest, if people order these, that'll probably be like a summer job for my kids to put all those components on the board because it takes a lot of effort to get them on there. With that, I want to wrap things up and speculate about the future a little bit. I think things could probably run faster in these devices. One idea, actually, I want to attribute this to David Nolan. He thought, well, maybe we could have an interpreter for Clojure or ClojureScript, just like Espruino is an interpreter for JavaScript. Maybe that leads to the same kind of performance trade-offs. Maybe one day we could have something that emits either C that could be compiled on any of these processors or WASM, because there's WASM to C compilers. Or maybe something like Babashka, a Growl native form of this could run. If it could fit on these smaller microprocessors, that would be really cool. With that, I want to just say thanks for watching this and thanks for your interest in the subject. All right, thank you.